Okay, I thought I'd make a little screencast here, a summary screencast of the probability section um, in the main, because we've spent a little bit of time doing it. And I've sort of let you go at your own pace, and we're trying to wrap things up now and find out what's important, what do we need to know. So on your screen at the moment, you see what's given to you in the formula booklet. Now this might give you a little guide as to what you need to remember, what you don't, and so if we just have a look through here, and mean set of data, that doesn't come up yet. The probability of an event, that's pretty straight, that's fairly self-explanatory, I think. This is the number of successful outcomes over the U being the universal set. So probability of event A, the number of A over the sample space, you could say. This is sample space. All right, and then we look down and complementary events. We talked about this word complementary. Sometimes whenever you see a question, at least find the probability of winning at least one game or whatever it is. You can usually find the complementary event is easier to find, and then you can subtract from one. So that's a useful thing. Combined events. So here we are, the union, the probability the A union B, A plus B minus the intersection, and that's where the intersection. If you think about that, that's the in the Venn diagram, the bit in the middle. Now, mutually exclusive and conditional independent events. These get asked a lot. So let's make sure we know how to do this, and this comes up in the revision questions. If you're asked to prove that the two events are mutually exclusive or not, this is where you're going to be heading. You're going to be summing their individual probabilities and showing that it's either equal to or not equal to the union. Although often it's easier just to show that the intersection, because if they're mutually exclusive, there is no intersection. There's no intersecting elements. So it might be easier to show that the intersection A, intersection B is the empty set. There's nothing in there. And if you've done a Venn diagram, that's pretty clear. If there's something in there, they're not mutually exclusive. If there's not, so for a Venn diagram, if anything exists there, if that's empty, then they're mutually exclusive. So if there's nothing in that bit there, this means the empty set. If it's not empty, then they're not mutually exclusive. And independent events, two events are independent if the probability of one times the probability of the other equals the intersection. And again, another way of looking at this is that if you've got a probability of A given B, if A and B are independent, then the probability of A given B will just be equal to the probability of A, because it doesn't matter. A is not affected by B. So this is another way of showing A and B are independent. Now that might be easier, or just depending on what you've done in the question or how it's framed or whatever else. So this is the stuff that you're given in an exam. Right, so if we have to have a look now over at the questions that you got here, we did sort of this one in class, and like I said, you can work through the first few parts, really straightforward stuff, but then it gets a bit more serious. Now this is the one, given that Bill wins at least one game, find the probability that he wins both games. So this is what I talked about in class. Now if I just go over this again, there were two ways of doing this. You can either use, you can use this, or is it even here? Yeah, this one here, conditional probability. So this one, written usually we sort of look at that as the probability of B given A. It's just a rewrite, is equal to the probability of intersection over the probability of A. Yeah, that's just a rewrite of that. So we can either use that, or we can use, here we go. Or we can use, as I like to do, use logic, but it's very difficult to sometimes explain that. So go through here. We've got, I think this is, what is this? 2/3 and 1/3 here, I think. All right, and I'll just pause. Now, I've just filled in the probabilities here for each of these outcomes. I actually find it useful to unsimplify fractions with probability so that you've got the same denominator right through. That means you can do a quick check, 2, 6, 10, 20, that adds up to 1. Makes it easy. So if you've got the same denominator, but also if we work through these questions through to part D, where it says, given that Bill, what does it say? Hang on, get back up here. Given that Bill wins at least one game, find the probability that he wins both games. Now, as I explained, right, we've already in part C, we've worked out the probability that Bill wins at least one game. This gets back to what I was talking about before. At least one game, that's probability of at least one game. That's equal to 1 minus the probability. What's the complementary event of at least one game? That's no games. Right, we can find that much easier. Probability of no games, who loses both games, is 1/15th, or 2/30. 1 minus 1/15, which is equal to 14/15. That's the probability of he wins at least one game. Now you can see how that flows into D. Given that he wins at least one game, what's the probability that he wins both games? Now for me, when I see that given, I think, right, that's changed my sample space. My sample space, so this is now my sample space. He wins at least one game. Okay, and I've just worked out that that sample space there is 14/15, or if we keep our denominators at 30, is 28/30. So now this is, my sample space has changed. That is my new sample space. In other words, that's now my denominator. Given that, so these are the only outcomes I'm now interested in. Now, how many of those 28 has Bill won both? Because that's what it says. Given that he wins at least one game, what's the probability he wins both? Well, if you break it down, of that 28, there's 20 where he wins both. There's 4 where he wins one, 4 where he wins one. So 8 where he wins one, and there's 20 where he wins both. So the solution to that, so the probability that he wins both, given he wins at least one, will be equal to, in my logical sort of working out, 20/28, which is 5/7. If you prefer to work through the conditional probability and use that, then you would be using, trying to change color here, you would be using the probability, where am I going? You'd be going the probability, this is equal to, alright, so sorry, you'd say that this is equal to the probability of the intersection, right? A intersection B wins both, intersection wins greater than or equal to 1, over the probability he wins greater than or equal to 1. So this wins both, intersection wins greater than or equal to 1. Well, that is just that 20/30, isn't it? So that's 20/30 over the probability he wins greater than or equal to 1. Well, that was the, what do we find that out to be? 14/15, or 28/30. So you can see either way, we're going to get 20/28 or 5/7. Okay, let's just have a look at, you got the solutions to all this stuff. So it's just a matter of me trying to pull out a question or two that might be helpful. This question here, I looked at 75. So for D, 75% of students learn Spanish. At this school, 50% of the students are girls. 85% of the girls learn Spanish. A boy is chosen at random. Find the probability that he learns Spanish. So I think for C, what we did here was we took, for G intersection S, we went 0.52 times 0.85 and got, I think from memory, 0.442. So in part 1, we're asked to find the probability of G intersection S. So we multiply 0.52 by 0.85 to get 0.442. So show that G and S are not independent. So I think the way to go here is to show that probability a student does Spanish given that they're a girl. Spanish given that they're a girl is equal to 0.85. And the probability that a student does Spanish is 0.75. Right, these are not equal. so not independent. I think that's probably the easiest way of showing it here. That obviously, we're told that 75% of the students learn Spanish, but 85% of the girls learn Spanish. So it's clear that they're not independent of each other, the gender and whether they take Spanish or not. So the easiest way of showing that is like the second, this method here, using independent events. In this case, we could have used the product rule and found that out, but I think easier here to show that these are not equal, that there is a reliance on the gender as to whether Spanish is taken or not. Probability of Spanish is 0.75, but the probability of Spanish given girl is 0.85. They're not the same, so they're not independent. Okay, then we came down to D, which I thought was a tricky question, really. We know 75% of the students learn Spanish. If a boy is chosen at random, find the probability they learn Spanish. Now, the way I thought about doing this, I took 100 students, and I said of those 100 students, 52 are girls and 48 are boys. Okay, these are girls and these are boys. Now, of those 52 girls, 85% of those 52 girls take Spanish. So I took 85% of 52, and I got what we got up there before, 44.2. So it's 44.2 girls learn Spanish, but of the 100 students, I need 75 of them to take Spanish, because 75% of my students take Spanish. So that means I've got 30.8 boys that take Spanish, and 30.8 divided by 48, right? 30.8 divided by 48 is equal to, what did I get? 30.8 divided by 48 gave me 64.2%. So 3 significant figures. That's the way I figured that out. You might have come up with a different method. Okay, I'm just going to do one more question. We do it's question 9. The number of boys. Okay, go right back up and sorry, just can't see the question there. There it is. There's 100 boys. 55 boys play football. I think they've got to take one or the other. 75 boys play rugby. So we add those two together and get 130. So there's a 30 overlap that goes in there. This is football and this is rugby. 55 play football, so I've got to put 25 in there. Rugby, there are 75, so 45 go there, add those three up. Okay, so once we've got this in place, find the number of boys who play both sports, and that's pretty straightforward. That's 30. The number that play only rugby, that's this 45 here, so that's all good. 9B, find who plays only one sport. The probability he plays only one sport, well, 70 of them, 25 plus 40, play only one sport. So part 1, that will be 70 over 100. And part 2, given that the boy selected plays only one sport, so now here's our sample space has changed now to 70. What is the probability that he plays rugby? Well, for rugby are 45 of those 70. So you'd narrow that down, and I'll leave that to you. And then I wanted to get down here, 9C. Explain why A and B are not mutually exclusive. Now remember, if they're mutually exclusive, there's no intersection. So you can just explain here that because there are 30 that do both, they can't be mutually exclusive. So 30 do both, although you'll be more eloquent, etc. I'm just rushing through. Show they're not independent. Now, so to show they're not independent, what we'll do is, okay, so to show they're not independent, all we need to do is multiply the individual probabilities. Probability they play rugby, we did up here, which was 9 over 14. Once it was simplified, 45 over 70. Probability that they play football was 25 over 70, if you remember, just football. So just rugby, just football, multiply them out, 45 over 196. Now, what's the probability they play both? Well, that was the intersecting areas, which was 30 over 100. And it's pretty clear to see that 3/10 and 45 over 196 are not equal, and therefore these two events are not independent. So I just wanted to show a couple of examples of how to actually answer these questions. 3 marks, how do you answer that they're not independent? This is the kind of thing you need to do. Mutually exclusive, you're looking for the sum or a zero or a null set of in the intersection. So all right, I'll leave it at that, and I'll see you on Friday for the test.